So Mary, if you want to come on up. Mary is going to be talking to you about AGN activity. She's coming from The Ohio State University. So thank you, Mary.
Hi, everybody. Thank you, Ren, very much for the introduction. So today I'm going to be talking to you about what I worked on this summer, which is looking at AGN activity in merging and non-merging galaxy clusters. First, a little bit about me. I am a rising third year at The Ohio State University, and I am a double major in physics and astronomy and astrophysics. And in my free time, I'm very engaged in outreach, especially for students in STEM. I play the guitar, and I also like to watercolor. So starting on with some of the science background, galaxies are massive systems of gas and dust and all of the stars and things that we know and love. And galaxies have supermassive black holes at their center. And some galaxies are particularly interesting to us because their supermassive black holes are active. And so they're called active galactic nuclei. And AGNs are byproducts of the matter accretion process into the supermassive black hole. And they're very bright objects. And sometimes they can even spit out material that can be larger than the galaxy itself and even brighter than the galaxy itself. Now, to look at AGNs, you can look at them in a variety of different wavelengths and learn different things. For our purposes, we're going to be looking at radio AGNs, and we're going to sort of break it down into two large subcategories, although you can go into even more subcategories. So we're going to say that a radio AGN can be a galaxy with radio jets coming off of it, or a galaxy with a compact radio detection at its center. And so the reason we're looking at radio is because both of these objects produce something called synchrotron emission, which we're able to see in radio wavelengths. What causes an AGN to occur? They're known to be fueling mechanisms. So it has to do with the actual black hole engine itself, which is within the galaxy, but they're also subjected to their fuel being compromised by the environment that they're in. So my project really hones in on the environment aspect of AGN fueling. And so galaxies can live in roughly two types of environments. So they can live in the field, which basically means they're galaxies that are scattered about and kind of live on their own and occasionally have passerbys and collisions. But galaxies can also live in clusters, which means that they're in a big group of galaxies and they're bound by a potential well. And the life of a galaxy in a cluster is a very interesting life, and it's very different from the life of a galaxy in the field. Because the galaxies within a cluster, not only are they subjected to the galaxy collisions and the galaxy-galaxy interactions of nearby cluster members, but they also have to navigate the dense, hot, diffuse intracluster medium. And so sometimes what can happen is as galaxies are moving around in the cluster, their gas can be stripped off. And so as they're navigating, getting their gas stripped off, they also have to worry about nearby galaxies, and all of those things can impact the galaxy's life. And so specifically, we notice that AGNs in clusters are especially impacted by this environment. So if we imagine the AGN is we have the plane of the galaxy and we have those radio jets coming off perpendicular to the center. If you take that same AGN and you were to put it in a cluster, what happens is those previously perpendicular jets can get bent. And this is because as the galaxy is moving around in the cluster, the intracluster medium and the gas acts as a drag force and can push those jets to be bent. And so that's one of the ways that we're even able to tell that an AGN, if you were to just look at an AGN, that's one of the ways you're even able to tell that an AGN is in a cluster is by these bent tails, because that's the only reason that you would see those bent tails. And so I just have an example. This is from our sample. This is a radio AGN whose tails have been so bent that it actually looks like one tail. And the way that we're able to know that it's one, it looks that it does actually have two jets is because we compared it with existing literature. And so if that wasn't chaotic enough, and if galaxies didn't already have a lot of things that they had to deal with when they're in a cluster, those systems can merge. So you can imagine that if you already have a lot of galaxy-galaxy interactions, When you now combine that with another system, you increase the amount of galaxy-galaxy interactions you can have. And so it's been well established now that AGN activity is heightened in merging systems. And so this transitions into what my research topic was this summer, which is to look at how does the large-scale environment, so a cluster, environment affect AGN fueling. And we specifically were looking at the AGN activity across merging and non-merging galaxy clusters. And so we're looking to see if we saw a heightened number of radio AGNs in merging or non-merging, their locations with respect to the cluster center, a heightened or lower number of certain types of AGNs. So kind of when we were talking about the bent tails, do we see a lot of those bent tails? Do we see a lot of those compact detections? Do we notice any pattern in merging and non-merging systems? And so talking a little bit about the specific research sample we used, we're building off of a built-in 20 paper where they looked at the merging and non-merging clusters that they defined, and they looked at the number of AGNs within those, and they found that merging systems had heightened AGN activity. And so what my project was to look at each of these defined AGNs to see if they had a radio detection, because not all AGNs will have a radio component to it. So we looked to see, we zoomed in on each of the AGN sources, and on the right, I have a large image of one of the clusters. I have plotted the known AGN sources and the non-AGN sources. So we zoomed in, looked at each of these AGN sources to see if we could find anything. And so we received a catalog from the authors of that paper, which included the dynamic classification of each of the clusters, and also their central coordinates, and also the AGN information of the galaxy members. And so we then looked across two frequencies. We used the Lotus survey, which is 150 megahertz from the low frequency array, so that we could look at the extent of the radio emission if it was detected. And then also look at the very large array Sky survey, which is 3 gigahertz, to look at a higher frequency radio emission. So that way we can learn a little bit more about the structure of the AGNs. And so once we had all of the images, I wrote a code to basically zoom in on all of those points and make a little cutout of those images, and then check to see for each cluster if the known AGN sources had a radio detection. And so compiled here, I have a comprehensive list of all of the radio detections that we found in the non-merging clusters. So we have this comprehensive tile for both frequencies, both the low and the high frequency. And we also have tiles for the merging and the non-merging, because our goal is really to look at the differences between the two systems. So with lots of images and lots of very large images, it comes as no surprise that my disk quota was obliterated multiple times. Thank you to the people that helped me multiple times to fix it. And so moving on to the actual classifications that we made. So we defined a radio detection to be within 1 arc second of the center coordinates, which those coordinates we got from the catalog. We defined a weak and strong detection depending on their contour level at a 4 sigma base. And then once we found a detection, we noticed a couple different patterns. So we decided to have a couple different categories within a detection. So we found some detections were extended, and we defined extended to be greater than 2 times the beam size of the survey. And for us, on the picture on the right, I have an example of how we went through the classification process. This is from the lower frequency survey, which our beam size was 6 arc seconds. So we have 2 times that, being 12. And so our mentality was, if we see emission that's larger than 2 times the resolution of the survey, then we could call that extended as a conservative statement. And consequently, on the other side, we found that a source was compact if it was less than 2 times the resolution. So we say something that's within that, we call it a compact detection. But we also noticed that there were some sources that we found in particular clusters that had a compact source, but also had some sort of extended emission. Now, it could be like a tail coming off on one end, or it could be just a large extension in general. But for the most part, we have the small scale extended emission. And so we came up with this hybrid of both of those detections. And so on the right, I have an example of something that has a compact center, but we see that there is small scale extended emission around it. And so we have some preliminary results. We tallied up the total AGNs we had, how many we had radio detections for, and then how many fit the compact extended and compact extended criteria based on looking at them so far. And so I'll preface this with, we have preliminary results because we are working with small scale statistics. And we do have a smaller sample size because not all of our clusters were covered by the lower frequency survey that we were using. But we found, based on just looking at the ratios, we found on average, we see more total AGN and radio detections in non-merging systems. And on average, we see more extended and compact extended emission in merging clusters. But as I said, these are preliminary results, and we're looking forward to enhancing our sample size so that we can get more data. But we're looking forward to the future where we're going to finish the high frequency comparison. And we're also going to look at the non-AGN sources that were in the catalog, among other things. But thank you very much for listening.
Mary, so we have time for a couple of questions. So if anybody has any questions, please raise your hand and go ahead and ask. For those on Zoom, you can go ahead and unmute, but we have one in the audience here.
All right, awesome talk. So for the compact extended sources, do you have any thoughts on what causes the perturbations to the shape?
I think that's something that we're still going to be looking into, because first what we want to do is we have to first localize where those compact extended detections are coming from. So are they coming from the merging systems? Are they coming from the non-merging systems? And then from there, I think we're going to analyze further to see what possible physical mechanisms could be.
It's just the extent of the jets. So some AGN will have younger jets. Okay. Extend as far. And sometimes, as she was saying, with the merging systems, you have a lot more chaotic activity, and so it can bend and twist the jets. But it's just hard to tell. Yeah.
Okay. All right, any more questions in the audience here? On Zoom, if you have, yep, go ahead, Major.
I'm curious, how did you, you define this classification? How did you go about it? Like looking image by image, or did you automate it?
For the detection classification?
The detection and also the compact or compact extended.
Right. So for the radio detections, like once we detected them and once we were trying to classify them, right now we have it to be, we're checking by eye, we're looking at it visually. But as you said, that's something that we're actually looking forward to in the future, is finding some sort of way to automate, maybe having a definitive size and flux, and then comparing that to see if we can have something automatically classify it for us.
Any more questions? Those on Zoom, you can unmute to ask. All right, if we don't have any more questions, thank you again, Mary. All right, next we'll be hearing from Lucy Steffes, who goes to the University of Wisconsin-Madison, and we'll be talking today about mapping neutral carbon. So go ahead and take it away, Lucy.
Okay, thank you for the introduction, Ron. So first, a little bit more information about me. I'm originally from Milwaukee, Wisconsin, but I'm now a rising junior at UW-Madison. I'm double majoring in astrophysics and physics with a double minor in math and German, and I've spent the past 2 years working with Professor Snez Stanimirovic, looking at different parts of the ISM. It's also my second summer as a GBO summer student working with Dr. Jesse Bublett, and I'm a 2022 Goldwater Scholar. Some of my hobbies when I'm not in school or doing research include hiking, photography, writing, and so on. So now getting into some of the actual science. The Helix Nebula, which you can see over there, is a planetary nebula, and it's actually the closest known planetary nebula to Earth. So it takes up a massive space on the sky and is very extended. But a planetary nebula is the outer layers of a former low-mass dying star. So over here, you can see a white dwarf star right there in the center, surrounded by a cavity of ionized gas. And those regions in orange and yellow that you see on the outside are mostly dust, molecular gas, and some atomic gas that were expelled from the outer layers of the star as it was reaching the end of its AGB phase. So I spent most of this summer studying neutral carbon, specifically the 3p1 to 3p0 transition of the 12C atom, which has a frequency of 492 gigahertz. So although the Helix Nebula is an oxygen-rich planetary nebula, we knew going in that there should be a lot of neutral carbon there. Specifically looking at the work that I did last summer, where I studied all of these carbon-rich molecules in the globules, 2 of the globules of the Helix Nebula, which are these small, compact little clouds that are extending radially away from the white dwarf star. But what's really important about neutral carbon is that it indicates the transition between the ionized gas in that blue region and the molecular gas in the outer regions, and is an important aspect of the photodissociation region. So speaking of PDRs, a PDR, or photodissociation region, is a cloud of cold neutral atomic gas, molecular gas, where most of the chemistry is driven by high amounts of UV radiation, which in the case of the Helix Nebula come from the central white dwarf star. So we see a couple of examples of PDRs here in globules B and C, which I studied last year. So they are compact pockets of molecular gas where a lot of the chemistry comes from the UV radiation and is pushing things backwards, and a lot of things are reacting right on the surface of that pocket of gas. It's also completely surrounded by a shell of atomic gas and ionized gas, which you can see there in the blue. So the globules themselves are generally very dark, that dark brown and black color, because at this frequency, they're not really emitted. So the data for this project came from the Atacama Compact Array, which you can see there circled. So it's a subsection of ALMA. The rest of ALMA you can see there. But because it's a compact array and is a smaller amount of smaller telescopes, you have a larger beam size. So it's slightly less results than you would get if you use all of ALMA. But because this region hadn't been mapped before, at least not to this high resolution, we didn't quite know what to expect. But the goal of this project was to look at these 6 regions across different environments of the Helix Nebula, 3 of them being globules, where they are these dense structures inside of the ionized cavity, 2 of them the east and west positions being almost as far out as you can go from the white dwarf star, while still being a part of the Helix Nebula, so being very diffuse, and then 1 of them, the rim position, being at kind of an intermediary stage, but also being obscured by dust, and then comparing this with molecular ALMA and IRM 30-meter data. Well, that was the goal. Because then COVID happened and 3 of the regions weren't observed at all, and 2 of them had a significant loss in the integration time, which for the west position resulted in us not being able to get a detection of neutral carbon because the noise was so heavy. Those 2 sources, east and west, also hadn't even been run through the ALMA pipeline, which is something that I got to learn how to do this summer. So let's look at some of the data. So first we are looking here at the rim position, which was that intermediary spot right there. So what's really interesting here is there's actually two different detections at different velocities. One of them being blue shifted from the systemic velocity, which is marked here in green, and the other one being at a lower intensity, but being red shifted. Now in purple behind there, we can see the HCO plus emission from the IRM 30 meter telescope. And it's notated here on this y-axis with neutral carbon being on this y-axis over here, just so that way you can see the different intensities. Now, what's super cool about this one here is with HCO plus, the intensities are about the same. That's definitely not the case for neutral carbon. And we're not totally sure why that is just yet, but we have a couple of ideas. One is just there's less neutral carbon at the red shifted region, but there's another idea that perhaps in between the two regions, there is something that's absorbing the emission from the red shifted region that's further back. Now, we don't have any evidence to support either of these theories yet, but that's something that we could look for in the future. So now looking at the east position, you can see that the signal to noise ratio is a lot lower because of that lower integration time, and possibly also because it's just a little bit noisier. But what you'll notice over here is there's a slight offset between the two peaks in the velocities between HCO plus and C1. Now we still know that they come from the same section because it is within the wings of HCO plus that we see the peak of C1 and the entire detection of C1, but it is just such a noisy spectrum that we could be missing something, and it could be something to look into in the future. Now here, being able to compare the two, we do see that C1 does have a much higher intensity at the rim position compared to the east position, but that's something that's generally to be expected here because the rim position just has so much more gas and such a higher density. So from here, I went on to map the two regions in neutral carbon. And I want to point out that here and that arrow over there indicate the angle that it takes to get to the central star. So for globule-like structures like those that we saw in globules B and C, they move radially away from the white dwarf star, which is something that we do see here where it's more extended and kind of creates a tail of gas. So we could make a conclusion that that could be a globule-like structure that's previously been obscured by dust. On the other hand, for the east position, it's really not following that angle towards the star quite as much, but it's still really noteworthy that we're seeing these different pockets of gas rather than broad diffuse emission that we might have expected just looking in the optical. So that could indicate that there's small little PDR regions that are home to all of the molecular gas that we saw, especially when we look at these contours. So these contours are looking at consecutive velocity channels to make sure that in the case of the rim position here, it's not just convenient pockets of gas that happen to be co-spatial on the plane of the sky. And we do see that this contour, which is about 5 channels wide, is showing that it goes through the entire piece here. So it's likely a globule-like structure. Now for the east position, I still put contours on even though there's not the dichotomy of velocities, but here are pockets like this one to show that it does still span about 4 velocity channels and not just convenient noise. Okay, so the last piece of analysis that I'd like to share with you all is a comparison to archival Hubble Space Telescope data. So in O3 and H alpha, I zoomed into the rim position. So it's the same position for both of these maps, and looked at the intensities of those two to see if they lined up with what we see in neutral carbon. So where there are bright spots, it's an inverted color map. So that's where there is a decrease in the emission. So you can see that generally speaking, especially in O3, there are regions that do follow about the same angle that we see right here. A little bit less so in H alpha, but if you squint and look between these two pockets of higher intensity emission, you can kind of make it up. But it becomes all the more clear when you add the contours on top from neutral carbon and see that it maps very nicely this region here and over here that goes in between the regions of higher intensity emission that that's likely where we're seeing those PDRs, and the ionized gas and higher energy emissions are going around the colder atomic gas. So just to summarize, we do see globule-like structures at the rim position which showcase a PDR, and it's the highest resolution mapping of C1 in the Helix Nebula to date. These globule-like structures were also previously obscured by dust, and we now know a little bit more in detail what is in that region. We also see smaller PDRs further out in the edges of the Helix Nebula, where we previously had expected there to just be broad diffuse gas. So all of this tells us that the Helix Nebula is evolutionarily complex, especially with C1 and PDRs being found so far away from the ionized cavity.
Okay, do we have any questions for Lucy in the audience? Yes, Larry.
Do you know how ultimately thick is the neutral carbon?
No, that's not something that we've looked into quite yet. There's some constants that I have to track down, but that's one of the things that I'm planning on doing next.
Well, I mean, the transition in general, is it an optically thick transition?
Off the top of my head, I don't know.
It's about the same optical depth as 13 CO2. So tau is one-ish or a few-ish.
So I was wondering kind of about the motivation of this. So when you guys got these observations and such, and you looked, were you expecting to find differences in the ratios of the molecules you were looking at when the clouds were in the ring or in the rim or in the east or the west? Or is this, were you expecting to find something? Or were you looking to confirm something? Or is this something that's unknown and this is why you're looking at it?
So we already had the molecular data. Jesse published a paper on that earlier this year. So the velocities, I knew more or less where to look for neutral carbon. But this feature was not something that we were expecting, the two differences in intensity of neutral carbon. Was there more to your question?
No, I think that's good. Yeah.
Okay.
The other thing is, this was meant to be a multi-component observation with like Sophia data. So we wanted to look at C2, C1, and our CO to try and constrain the actual carbon content.
Yeah.
But yeah, our Sophia project got rejected. So
Yeah.
So when I see the spectrum on the left, I see an expanding shell. Is that what's causing those two velocity peaks?
I think so. So the Helix Nebula is generally expanding with winds pushing everything outwards. And there is still debate as to the chemistry that's happening. If everything is being broken down and returned to the ISM, or just staying at the molecular and ratios that it's already at and expanding. But yeah, everything is expanding. And right now we're kind of looking down the barrel. So there's an offset in the different velocities, but it is all moving outwards.
So the blue shifted component is presumably on the near side of the shell and the red shift on the back side of the shell. So you wouldn't expect any correlation in morphology between the blue and the red.
Do we have any questions on Zoom? Okay, Pedro.
When you were mentioning possible scenarios to explain the difference in the ratios, you mentioned that the redshifted one would be be absorbed by something, what would this something be causing the absorption?
So there could be some sort of cold gas in between the two features that could be taking in some of that emission that's pointing towards us and absorbing it and then re-emitting it somewhere else. But because we haven't been able to look at that and, for example, map in HCO plus where we see that we are getting equal or more or less equal intensities between the two positions. So that could be something that we could do to confirm or deny if there is an absorption feature, would be mapping it in the molecules where we do see equal intensities at both points and comparing that with the mappings of neutral carbon. But we just haven't quite gotten there yet.
That's all the time we have for questions. I'm sure if any more questions come up, Lucy would be happy to answer them after. So thank you very much. All right, next we have a talk from Corvus, and Corvus will be talking from Texas Tech University, and Corvus will be talking to you about large bound atoms in space. So take it away.
Yes, all right, thank you, Gwen. So for this project, I have been working with my mentor, Dr. Peter Salas, on it. But before we begin, here's a little bit more about me. So I'm a rising senior at Texas Tech University. I'm a physics major with minors in German and math. The first being made a lot easier by the fact that I'm a German native speaker. I've also lived in the Middle East for a few years, and while there, my family adopted our cat Frankie, who is honestly just my baby, and I miss him. But that being said, I have been having a fantastic time this summer, getting to go up on the GBT and down to the fallout shelter of the Woodford Folk. When I'm not out exploring with the other summer students, I've been reading, doing scratchboard art, and painting. That's enough about me for right now. So when I first got here, I'm pretty sure I asked Pedro at least 5 times how the title of my project actually tied to the work that I'd be doing. So essentially, the largest bound atoms in space, also called Rydberg atoms, have large bound atoms, also called Rydberg atoms, have high principal quantum numbers, something like n over 100. And this can mean that these atoms have diameters of up to 3 microns, which is huge for atoms. Essentially, this is a highly energetic electron that causes its radius to be so large. So for my project, I specifically studied atoms that form as a free electron combines with a free ion before being stimulated down energy transitions by an incident photon before eventually emitting photons we can observe before being separated again. Because this process happens over and over, as the electron and ion combine, separate, and recombine, these emissions are known as recombination lines, specifically radio recombination lines, as they are visible in the radio spectrum. So RLs are extremely sensitive to the physical conditions of the gas in which they originate due to the process by which they form. This means that they offer a unique look into the interstellar medium, especially as radio observations are extinction-free. Now, for this project, I specifically studied hydrogen RLs around the W43 complex, which is a star-forming region containing a giant H2 region surrounded by diffuse ionized gas. You can see here in this image the H2 region very clearly, and this box represents the location of my data. Now, it's not entirely clear how these two regions, so the H2 and the diffuse ionized gas, interact with one another. We know that the diffuse ionized gas is, well, ionized, but we don't quite know the source of that ionization. Although it's known that H2 regions do leak ionizing photons from their region, the details there are also still relatively unsure, and there could be multiple sources of ionizing photons. Ultimately, this is something that this project hopes to shed light on, characterizing this diffuse ionized gas and hopefully providing more information about these interactions. So to actually begin using RLs to study the data, this region, I use data from 2 surveys, specifically the GBT diffuse ionized gas survey, or GDIGS, and GDIGS at low frequencies, so GDIGS low. This rectangle in the bottom corner here represents the data that I used for this project. It is the very first data from the GDIGS low survey And as a result of this data being so new, some of the maps that I've shown here today will have a slightly different shape due to receiving a better processed version of the data as we continue working more with it. Now, GBO at 340 and 800 megahertz was specifically created to be a low frequency counterpart to the GBO REU at 5.7 gigahertz, which you no doubt guessed by the names. Love astronomers naming things so bluntly, it's amazing. So the reason for this, though, is that high and low frequency comparisons allow us to study the density and path length of this gas. And for my project, I specifically focused on density using the 800 megahertz data from GBO and then the GBO data. There are, however, some complications that arise from using two datasets, namely that we had to reproject the GBO data onto the GBO data in order to smooth it to the same spatial resolution, which is about 17 arc minutes per GBO, but only about 2 arc minutes per GBO. So to begin working with the data, I created 3 moment maps using the GBO data in the velocity range of 60 to 140 kilometers per second. Each of these maps shows a different information. This one specifically is a moment 0 map, which shows the intensity of the emission integrated over the spectral channels. The middle map is a moment 1 map showing radial velocity of this gas. And the one over here is a line width map, or the full width half max map, which shows the width of the emission lines at half the vertical maximum. This one studies random gas motions and non-thermal motions, and does look a little bit different from the others due to the way that it's computed. Next, on this slide, we have similar but also very different maps. They are still moment 0, 1, and full width and line width maps, but this time they have been created using both GBO and GBO data. This is also why the overall shape is different. Comparisons can only be made where both surveys have data. For example, using the GBO data, this is the moment 0 map, then this is the GBO moment 0 map, and together, when combined, they form this ratio map. So speaking of ratios, both the moment 0 and line width map are ratio maps, meaning that I divided the low by the high frequency data. And the moment 1 map is a difference map, where I subtracted the high from the low frequency data. So going back to this moment 0 map, this one again just shows the intensity of the emissions, and specifically these central values are around 10, meaning that the emissions that we see in the low frequency data is about 10 times as bright as those same emissions in the high frequency data. For the moment 1 map, the central values are around 0, so we can assume that the gas is moving at roughly the same velocity. Then for the line width map, the values are around 1, so we can assume that the emissions are about as broad in the low as in the high frequency data set. Now, the overall goal of my project was to create density maps, but there's one very important assumption that we had to make first. Is the gas being studied? Is the gas studied by both these surveys the same gas? Meaning that spatially, did they survey the same gas instead of one of them just catching a cloud line of sight, for example? So to do this, we look closer at this moment 1 difference map. Again, the central values are around 0, and these smaller blue tints are not statistically significant. If they were, we can conclude that, okay, this gas probably isn't the same, but it's not. So that's a good thing, right? Unfortunately, this by itself is not enough to conclude that it is the same gas. Unfortunately, though, at this stage of the project, this is the only check that we essentially have for now. And so we move on to density. Now, studying the density is important for a few different reasons, namely that we can use it to study relationships. For example, the relationship between electron density and, sorry, 1 second, electron density and I think molecular clouds or something like that. And then also how the ionizing photons leaking out of H2 regions affect the interstellar medium. So this is it. This is the density map. Great, right? Well, okay, yeah, to look at it, it's very good. I used a peak ratio model, so where I compared the peaks of the emissions in the high and the low frequency data, and then essentially worked backwards to create this density estimate. On some level, yes, it's very good. The values that we see here, especially here in this region, is about the few tens of electrons per cubic centimeter, much less dense than expected densities in H2 regions, and yet more dense than very diffuse gas. This basically confirms that, yeah, we are studying what we want to study. It's also interesting because we do see some variations in this gas, meaning that this isn't just a flat generic layer, and could be very interesting to study further. That being said, it's far from perfect. You have here this artifact where the observations overlap, and all these bright yellow blobs where there's this extremely high estimated density. Why is that? Well, unfortunately, the model itself that we're using has some limitations. It assumes a constant value for background continuum and temperature, which realistically isn't the case, especially near the edges of our data. Not only that, it's actually the second version of our model, which already mitigates some baseline issues that we had previously. Ultimately, though, this is still very good. It provides some information and will also let us push for further studies in order to improve our models better and get a better understanding of this map that we have created. Before I wrap up, however, there's one last thing to discuss. Carbon detections. So this here is a spectral line image comparing the GDIGS and GDIGS low data, where the low frequency data has been scaled down by a factor of 11 to make it more visually comparable. Hydrogen and carbon have a velocity offset of about 150 kilometers per second, represented by these blue lines here. And when we specifically look at this area, we do see that, yes, there is a carbon emission. Well, okay, so what does that mean? Carbon is actually a very unique probe of gas that is dense to other probes because carbon is more dependent on temperature. Not only that, but carbon is more visible at lower temperatures. So, for example, carbon can still be ionized when hydrogen is actively forming molecules. This can help us study the formation of molecular clouds, which then ties into star formation. So overall, radio and combination lines are more intense at lower frequencies. The density model that we have is very good so far, but has a lot of room for improvement. Carbon emissions can be used to study the formation of molecular clouds. I would like to emphasize, though, again, this is only the beginning of the GDIGS load survey, and we can expect similar analysis to be performed for the rest of the data. I would like to thank Peter for being an absolutely wonderful mentor this summer, and I've had a great time being here. Thank you.
Orvis, do we have any questions in the audience? Jim?
I have a question. So a typical molecular cloud has a density of, say, 100, a couple hundred particles per cc. So this is much less dense.
Yes.
What, is there any correlation between the structures you see in the molecular gas in the same image?
So for this one, I'm not entirely sure. We are still limited, that it's kind of hard to see what structures we have because of the artifacts in this. And I think the overall resolution of this isn't very good. And I haven't done enough research into molecular clouds myself to be really able to answer that further.
So my question could be, so are you seeing the skins of molecular clouds, or is this stuff between the molecular clouds or totally unrelated to the molecular clouds?
I'm not entirely sure how to answer that right now.
I don't think we know yet.
Okay. That's cool. I mean, it's good.
Yeah.
Curious.
Yeah. So I was wondering, so in the beginning, you showed that nice image of there were the two diffuse clouds, and then you have your two GDIGS slices. And so I was wondering, so yes, okay. So these slices, how are those related to the individual clouds that you showed in the image before? So are these those? Okay. Yeah.
So what we're seeing here in this image is specifically a color composite image of the H2 region. So this is basically what we're looking around kind of in this in the box that I've basically outlined, which then transfers over to this box as well. So we're basically looking around that H2 region.
Okay, so it's just kind of taking a middle stripe out of the box.
Yes. So this blue line for the GDIGS load survey shows where data will be taken. Which is why that mine is a rectangle. And this is basically just a prediction based on the pre-existing data of GDIGS.
Okay.
That answer your question?
Yes.
Okay, perfect.
Any more questions in the audience? If you have questions on Zoom, you can unmute. I can't currently see the chat, so if you unmute and ask. All right, any more questions in the audience here in person? No, all right, thank you for that. Oh, that's okay, we can do it here. It has to be uploaded. We can probably do it on the computer. Yeah. me see. All right. So next we have Amara, who's going to be talking to you about solar panels and sun tracking. So thank you, Amara.
So, hello everybody. I am a rising junior at Rose-Hulman Institute of Technology, where I am studying mechanical engineering with a concentration in aerospace and a minor in Spanish. At school, I am on our underwater robotics team MATE, where I get to drive this lovely creation. Its name is Duck. So I'm a pilot, and I've played the cello for 9 years. I have 2 cats of questionable intelligence. Their names are Bumble and Bean. Let's see. So my project was to make a sun tracking solar panel that we can use here at the observatory as a prototype. So this project has changed quite a bit since its inception. When my mentor and I first started working on it, it was just to make a simple solar panel for the visitor center or for visitors to look at and learn about solar power, but it has kind of evolved. And so now it is to make one of the sun tracking so that we can kind of investigate how maybe in the future we can incorporate the observatory could incorporate a solar array here to promote sustainability and help offset some of the power that the observatory uses. So one of the things that we were really focusing on when we were making this was to make the solar panel something that can be self-powered. So the power that it gathers from the sun can be used to drive it as it tracks the sun, but it can also generate power at the same time. So some of the things that make a solar panel efficient, efficiency is influenced by a lot of factors that are larger scale, like the latitude that the solar panel is placed, the season, the weather, obviously, and also things that are more specific to the panel, such as the materials it's made out of. But one of the most important ones is the angle between the solar panel and the sun. The closer it is to the sun, the more power it gains. And it gathers the most energy and creates the most power when you're directly at the sun. And the sun's rays hit it at a 90-degree angle. Sun misalignment doesn't impact the power much, as reflections of the rays from the ground and from the sky itself still provide quite a lot of power. But over the course of the year, a fixed panel, which can't track the sun, especially during seasons when it's higher or lower in the sky, and at sunrise and sunset when it's at other ends, eventually lose efficiency and generate less power. So yeah, so the panel that we were making is a 2-axis tracker that follows the sun in azimuth and elevation, and then uses an internal list of sun positions with date and time to follow it over the course of the year. And over here you can see someone else's experiment looking at how much power is generated when we use sun-based track versus with a steady panel. So, design. The theme of this presentation is rendering errors. So good luck if challenge students to try spotting them all. So the basic design is an array of panels at the top, which is formed of 6 smaller panels that together generate about 11 volts at 0.6 amps for about 4 watts of power. Central section, which supports the panels, which is made of a column that also contains the differential drive that moves them in azimuth and elevation, and the base, which includes all of the electronics minus the solar panels, and an RFI enclosure that keeps that helps keep the equipment here safe. The panels are driven by 2 electric servos, which is basically a DC motor with position control built in. These were chosen for their lower power consumption and lower noise than the alternatives, which is usually stepper motors, which create much more and are more power hungry, with the trade-off of producing a slightly lower torque. Now, on their own, the servos that we used here actually don't have position control built in, but they have a lovely position sensing system, which I use to write a control loop that reads the position and then uses a PI control loop, which uses the error between the measured position and the desired position, takes the proportion of that and the sum or the integral. PI stands for proportional integral control, and then uses that to adjust the speed of the motor so that we can control the position exactly instead of trying to waffle around it. And the panel said it uses 2 of these in a differential drive system in order to drive servos. Differential drive is basically, here's the system. This is the central pillar column that supports the panels. Up here is the pivot structure that the rod the panels are on goes through. Here is the 2, in here is 2 concentric cylinders that are actually not mechanically linked except for these 2 gears, bevel gears up here. Each cylinder is driven by one of these gears down here and one of the motors. And if we cut this in half, we can see that highlighted in red is the inner one, and outside of it is the outer one. And the pivot and upper view are not shown in this picture. So by engaging one or both motors and one or both columns, we're able to create the different kinds of rotation we need. Here we can see that demonstrated in elevation only. The outer column has been cut in half so that we can see the inner one as well. In elevation, please. Here we go. You can see that the outer, it's hard to see, but the outer column moves with this lower gear, and the whole panel arrangement moves in elevation. If we move only the inner one, the panel moves in azimuth and elevation at the same time, as the horizontal bevel gear here is kept static, but the rotation of the pivot meshes the vertical gear, moving them into at the same time. And oops, come on, there we go. And finally, for azimuth only, we move the two columns equally. So that's called the differential drive. The motion up here is determined by any difference in the rotation of them at the bottom. You can see that they don't really rotate relative to each other here. This system has some pros and cons. On the one upside is it allows all of our electronics to be kept in the base where they can be enclosed in an RFI enclosure. They also allow for very flexible, the panels to move very flexibly, as they can move in a lot of different combinations very easily. And the motors, the servos have a rather low torque, so they don't have to hold the weight of the panel assembly like they would in, say, the GBT, where the motors are without brakes, responsible for keeping the assembly from slipping. Unfortunately, it's rather hard to program this to work in a way that is good instead of a way that works. And because the 2 columns don't extend into the box so that they can remain isolated and keep the RFI within, supporting the columns and making sure that nothing tips over is rather tricky. No. All right, so down in the base, the whole array is controlled by a network of circuitry and boards. Everything was programmed in Arduino, which is chosen because of wide availability of libraries and components that are compatible with Arduino that are very easy to all put together and ease of prototyping. The microcontroller is a big thing, which is chosen because it's very low power consumption, as we wanted this to be, well, generate as much power as possible without consuming much. Also contained in the base is a compass and an accelerometer, which are, because this is a portable prototype, so the prototype can be placed down essentially anywhere, and it would be able to find where north and south are on its own, because it doesn't actually look for the sun. It just goes off of an internal base of some position. So that when placing it, you don't have to yourself find where south is, make sure it's flat, stuff like that. Also contains the battery charging circuits, and a clock circuit, so that in the event that the batteries die or the controller is disconnected, it still knows what time it is. And down here, we kind of have like a flow chart just detailing where the information is flowing with the system. The microcontroller gathers information from its own storage, where the sun should be, as well as the compensating accelerometer. Uses that to command the motors to move, which of course has feedback that tells them where they are. And all of that is then used to move the panels to the correct positions and gather power. Now, all of this is quite a lot of computers and components in a prototype for something that could very feasibly go next to a telescope setting. And so, of course, for all of that, we need to mitigate our RFI. In real application, this would be especially useful because most of our power runs on AC power, but solar panels generate DC, and the inverter, the component that converts the two, is very noisy in RFI. So this is a pretty critical component. As well, one complicating factor for this was that the torque from the motors has to get out somehow. And until we have electronics that can do telekinesis, this has to be done physically. And so there has to be some hole in the RFI tight box to get the shafts from the motors out to drive the columns themselves. And we accomplish this by including within the box a waveguide below cutoff, which is essentially a tube that has a certain radius, and determined by the radius and the length. Any signal below a certain frequency is attenuated before it can exit the waveguide. So I originally had rendered some here, but I found in the lab, at the back of the Jansi lab, an actually very good demonstration of this. This is one of the RFI type computer boxes there. And you can see here, the structure is a waveguide. And there are, in this case, there are wires going in that then come out so that they can exit without contaminating the surrounding environment, RFI. Future work, there's quite a lot of it. While we've made a rather thorough model of all of the parts and how they go together, there still is making it to be done, with a lot of delays in, a lot of time constraints and delays in manufacturing that prevented us from really doing much of that. So the main ones would be to manufacture all that put together. We'd also want to test how well the RFI mitigation works. The waveguides, as you can see, they will be here, are test how efficient they are and how much they actually work. As they can't be too thin, the thinner they are, the better, the lower the cutoff frequency. Higher the cutoff frequency, that's not bad. But if they're too thin, then the axles that go through them will be flimsy and not really hold up over time. Also, in the future would be weatherproofing, as is based on the holes, is not a particularly weatherproof object, which would be rather desired and something that's meant to go outside. And also, once it's all together, we could be able to measure the power consumption and how much, whether it can actually be able to power something else or even itself. But for now, we got a very good model so that we can start working off of two things.
We do already. I'm like, how big is this? Like in comparison to a person?
This, oh, let's see. This box is 6 inches tall.
Oh,
So I think, I cannot remember exactly the dimensions of the panel, right?
okay.
But
It looks it's kind of small.
so I think in total will probably be 1.5 to 2 feet tall.
Okay. Nice. Larry.
You kind of already addressed this. How confident are you that the extra power generated will be enough to power the thing, the tracker itself and related instrumentation?
Well, all of the parts were chosen to be to consume as little power as possible.
Is it kind of a build it and we'll find out kind of experiment?
Sorry?
Do you think, is it kind of a we'll build it and then find out experiment, or are you pretty confident that it will?
Based on with the panels generating max power, it should be very well able to power itself. It's more a question of, in practice, how much the panels actually generate with, you know, manufacturing defects with shade on average and stuff like that, as well as one factor is going to be how much friction and how efficient, how able the motors are to move the structure. The motors aren't on all the time, so it's like over time whether it'd be able to power itself at any given moment it would be. But there are some things that, yeah, would need to be tested in real life.
Do you have any questions on Zoom? Feel free to unmute yourself and go ahead and ask.
Yeah, I actually do have a question. First of all, that was a great talk on where I learned a lot. That's really cool. So my question is just, this looks like a really, so it uses like kind of off the shelf components mainly, it looks like, I guess, at least for the Arduino and that part of it. So have you and Walter thought at all about like, you know, at some point turning this into like an educational project as well, like for students? Or yeah, I was just curious about that.
We haven't, although that could be a really interesting exercise.
Oh, Pedro, go ahead.
Curious, does the panel go all the way national? Does it have, can it just keep spinning, or does it have like unwrap the cables like a telescope?
So theoretically, it could go all the way in azimuth because the motors themselves have no limits, but in practice we would implement and have limits on how far the motors are allowed to move, so that the wiring that comes from the panels to the instruments and base can deal with that.
I'm curious how much planning you did with the actual aiming of the panels towards the sun. Did you do any calculations about how accurate you think that could be with these servos and based on the models of where the sun will be?
We did a bit with that. So, well, so this is we were testing how well the servos can respond to load if that impacts their position control at all. And the control loop is designed so that it will always be going for the position it's supposed to be at, and it can tell when it isn't. And with this, the testing we did get done with this seemed to confirm that. It just kind of makes the trip along the way a little bit more interesting. It should be able to, but it would be a thing that we need to test.
Okay.
See exactly how well it does do that.
Okay, so the feedback loop, like the back portion, is purely from the servos themselves, where they think they should be versus where they think they are. Or is there? Does that make sense? There's not like a sensor that's saying, well, I know. I mean, you're talking about this compass as well, but I didn't know if there was another sensor.
No, yes.
Of...
There is a sensor. These
Okay.
servos contain a essentially do contain a position sensor.
Okay.
But they don't contain this. They're not inbuilt with the position control.
Gotcha. Okay.
There's no external light sensor. That's what we want.
Okay.
Yeah, the position of the sun on any given day is stored within the regular controller.
Gotcha. Cool.
I think that's all the time we have for questions. If you have any questions after this, feel free to reach out to the summer students, and I'm sure they'd be happy to answer your questions. But thank you again. One more talk in this series. I believe it's on August 23rd, and that will be from Catalina, and it'll be at 2 p.m. in here. So one more in the series, and thank you again for all of you for coming. Nice job, you guys.
Yeah.
Thank you, girls. I was gonna know, we're going to be Saturday. Yeah, they have to. Yeah, so it's early, but yeah. So we'll see Saturday morning. We'll be just there.
So we can go at
Yes, 7.
Yep, that's what I was.
Yeah.
didn't expect that. Sorry, but I did that. No problem.
Okay, boy, laptop.
I can admit, for us, I did spend 2 minutes to start into a tap dancing routine
Okay.
All right.
I'll be right.
Sounds good.
You're very dapper. It looks like you're wearing, a tuxedo. And then the fact that your mask is black as well. Yeah. And so when you're standing there,
Yeah, no,
I just think that
I can feel myself standing in the position. Like, no, stop standing like that. Also, I briefly started on the comparison, like, because I realized I forgot to say the word on that mask.
Brian, let's see it. What? Yeah, I was reading that my plane is on 18. I said, not 19. I think I won't be able to see your presentation. I'll be in a trip. Right. Out of nowhere. Congrats for your presentation.
I didn't know that until you showed me that yesterday.
Thank you for the wonderful introduction.
Good. You guys all did really well.
Thank you.
You took pictures. Hang up the Zoom.
Oh, yeah, it's the side dish thing. So
At 7.
So come to the house, you're gonna have stuff.
Yeah.
Because
So.
I was like, I've never used it before. And I was
Yeah,
like,
just have to.
honestly, don't worry about it. I want to know. We can just watch the together. Remember, because they tried like this. I think so, yeah.
Yeah.
Yeah.